Today we are doing Vodcast 26, in which we discuss some of the ideas in section 9.2. The topic of 9.2 is boundary characteristics. And you'll find that this chapter is a little bit mathy, and we talk a little bit more about modeling. So I'm going to spend a few minutes just talking about what is the difference between the boundary layer and other layers in a fluid flow. And then I'm going to give you some hints for getting your homework problem done. On the video today, I'm going to do problem 9.24, and then I'd like you to use the material from 9.24 to do your homework problem 9.25. However, I would like to preface that by saying that the concepts of boundary layer are fairly intelligible without getting too much into the math. So we'll need to do the math for your homework, and you'll need to be aware of the mathematical relationships. But we can also talk about what happens in a boundary layer and what it looks like without going into that discussion. So that's how I'm going to approach this, is sort of from a conceptual point of view, and then give you hints for getting your homework done. So first of all, when we talk about a boundary layer, what exactly are we talking about? So I'm going to come over here to the podium PC, and this is an article from Wikipedia where we talk about the boundary layer, and it's actually very good. But basically, what happens is that you have a layer in a fluid as it's moving that's in the immediate vicinity of a wall of a pipe or whatever it's flowing through or over, where the viscosity effects of the fluid become significant. Now, the way that the boundary layer looks in laminar and turbulent flow looks significantly different. And so we've also talked about the fact that with turbulent flow and laminar flow, the Reynolds numbers look significantly different. So you can determine whether you're in a laminar or transitional flow by taking a look at the Reynolds number. Now, when you look at the the boundary layer, where those viscosity effects are important becomes a very important idea for how you model a fluid flow, and also for how you determine what are the most important characteristics of that flow for a particular application. So, for example, if you have aerodynamic flow, there's actually a different set of equations, or a specialized set of equations talking about aerodynamics, because it becomes very important what goes on right in the vicinity of an aircraft wing and airfoil in order to determine what the flow is going to look like. And of course, what the flow looks like determines how much work you can do by putting air above and below the wing, and therefore how much work you can do and how much lift you can get out of that particular flow regime. So when we take a look at these ideas, we have to go back and remember what Reynolds number is, because Reynolds number will help us to determine whether we are in laminar or turbulent flow, and that will give us some other ideas about where the boundary layer is, how thick it is, what its relative thickness is to the thickness of the conduit or the dimensions of the fluid flow. So if you recall, the Reynolds number is that dimensionless ratio, and the equation for Reynolds number, which we have to split it up, of course, and look at it differently for different types of flow and different flow regimes. But basically, Reynolds number is a dimensionless dimensionless constant formed by that dimensionless group. And so when we start talking about boundary layer characteristics, what we're basically doing is we're dividing the flow into a viscid and an in-viscid region. So if this is a pipe or a conduit, you'll have some region where the viscous effects are important, and then generally speaking, between the viscid layers, you will have an area where you can treat the flow as inviscid or ignore or minimize the effects of viscosity. So as you go through section 9.2 in your textbook, you'll see some fairly important equations. And beginning with equation 9.3, equation 9.3 is on page 546 of your textbook. Let's see. All right. So I'm going to switch over to the podium PC again. All right. So when we take a look at this equation, we're talking about a displacement thickness. So we're referring to figure 9.8, where we're taking some del in the y direction, and we're equating it to the velocity, where the velocity profile in this case looks somewhat parabolic, and in this case we have sort of a flat u, which would be, in this case, the maximum velocity. But these are the equations that we start looking at in terms of our analysis. So I really like the picture down here in example 9.3, where you can see that we have some place where we have an entrance, and the viscous effects on the entrance into this flow regime is basically inviscid throughout. And then as we go further and further, the viscous effects near the wall become more and more pronounced. So on the outlet of this conduit, we have a sharply defined, it's not really parabolic, but we have, you can sort of see just by the function of the velocity that we have a viscous region where we have a cling here at the end where we have that no slip condition, and we build up rather quickly to some average velocity which remains basically constant in that core of inviscosity or inviscid flow. So the solution here relies on some of the ideas we've had in the past, but we also equate it to the flow equation for del that we just talked about. So when you're doing your homework, section 9.3 or example 9.3 is also a good place to start. Now, if we continue talking about, let's come back here, the boundary conditions, 9.2.2 talks about the Prant-Blasius boundary layer solution, and we're not going to work with this very much in our studies. We kind of go straight to the Navier-Stokes or the Navier-Stokes, and we've looked at these equations before, but we start, there's actually a term missing here. It should equal 0. So I'm going to write this up. Equation 9.8 in your textbook. Here just says du dx plus dv dy. That should be equated to 0. So check your textbook, and if it's not there, we need to make sure that it is. So du, or del u, del x, plus del v, del y equals 0 is what equation 9.8 should read. And of course, when you look at your textbook, if it looks like my textbook, it's not even an equation, it's just two terms written together. Similarly, oh no, we're good here. Okay, so we have the partials times the velocities in those directions equals this second partial. So that one's fine. That one's written correctly. 9.9 is written correctly. All right, so it goes on to discuss some of the consequences of these equations, and we conclude for this little part that the boundary layer equations can be written in terms of a similarity variable. So what we're doing really is talking about how we're going to solve those differential equations. All right, so we have a specific condition here where we have to take into account what Reynolds number looks like for laminar flow and for turbulent flow. And of course, it gets much more interesting for turbulent flow, but the laminar flow equations are somewhat easier to follow. All right, so we have different boundary layer profiles depending on what type of equation systems we use to solve. But the next important thing that we need to talk about is the momentum integral boundary layer equation for a flat plate. Now this is obviously a very specific condition, but it's an approximate technique to analyze a boundary layer flow. And with these very complicated differential equations, we're always looking for ways to solve them. So if we talk about the momentum equation, and we write it out in the form shown at the bottom of this page, we can take a plate of width b, whatever b is, just some random value, and we can solve using just a summation of forces in the x direction equaling those drag forces. And we come up with an expression in shearing stress, which makes sense if you think about the orientation of a shearing stress considering a tau. So if you have a shearing stress tau, that is always a function of some sort of parallel forces or forces parallel acting on a surface, and we know that that's not a bad representation of viscosity. So that sort of all makes sense. All right, so then figure 911, we have another control volume. Let's see if I can get rid of this now. There. We have another control volume problem where we take a look at a streamline and a boundary layer edge with that velocity profile again. So one of the things I'd like you to see is that we keep seeing the same sort of variables and factors every single time. All right, now there's a statement that tells us that the drag on a flat plate is related to the momentum deficit within the boundary layer, which also makes sense, but this equation, 922, actually expresses that mathematically. Okay, so if we continue in our textbooks and we take a look at page 558, we also see a graph here that plots y versus del, which is how far we are into the pipe. So you go from 0 to 1, so you can see this is a dimensionless constant of a distance over the total distance. And then we have u over u, which once again is a dimensionless velocity term. And we can see that we have different boundary layer profiles that are based upon the momentum integral equation depending on the shape of that profile. All right, now the other thing that they talk about here is a local friction coefficient, and we define that as a function of tau and rho and the maximum velocity in that profile, and we can come up with a local friction coefficient that, as we can see, is pretty simple formula based upon the Reynolds number for the velocity solution anyway. And then if you look at the table, you'll see some other solutions for that as well. So as you're doing your homework, this is the sort of thing that you would look at. And we're talking about laminar flow here. So then as we proceed through this section, we start talking about turbulent flow a little bit. And there's just basically some information about turbulent flow that really becomes mathematically very, very complicated. So on on example 9.6, we have a function of tau, or tau is a function of u and v and del. And they give you a graph, which once again, just like with Reynolds numbers or any dimensionless coefficients, having charts that will allow you to find values based on different dimensionless groups is always a big solution in hydraulics. It's a good way to reduce these equations to something that's pretty usable. All right, so then the last graph that I'd like to show you, let me blow this up because it's pretty important. Oops, there we go, is if we have that Reynolds number plotted against the drag coefficient, you can see that the functions look different. If we're laminar, it's quite simple. And then if it's transitional, we have some different, completely turbulent, we have some more complicated relationships. So in between laminar and turbulent, we're going to have this transitional region, but we can find the friction drag coefficient based upon the Reynolds number, in other words, based upon the degree of laminar, transitional, or turbulent as we can define that flow. All right, so the final thing that I would like to do in this chapter is to take a look at problem 924 and then ask you to use that as a model for doing problem 925. So problem 924 is in your textbook at the end of the chapter on page 611. I hope this doesn't make you dizzy. As you can see, there's a lot of chapter 9 that we don't cover. It gets a little bit strange, so we're just kind of doing a little introduction. And depending on what field of engineering you go into and what class you go into next, you will be able to use parts or all of this more intensely. All right, so 924. We have a laminar boundary layer velocity profile that looks like this. U over U is this function. For y is less than or equal to del, just meaning that we're between the boundaries of the plate, and u is equal to u for y is greater than del. All right, so at some point then, we're going to expand beyond del, and we have a different velocity profile, don't we? It's just going to be constant. Show that this profile satisfies the appropriate boundary conditions. All right, so if we take a look then at how this problem works out, problem 924 looks like this. We start with our equation that we are given for u over u, knowing that that's for this, for y is less than or equal to del, and that for y is greater than del, we're just going to have a constant velocity here. So we really have two things that we're showing. So this has the form of a mathematical proof. So we do a substitution so that we can work out this equation a little bit more simply. So we have this and this. This is required, and this is required. And so therefore, when you go through the math in this way, putting in the appropriate numbers, we have the appropriate boundary conditions are satisfied. All right, so for part B, it asks us to use the momentum integral equation to determine the boundary layer thickness for del is equal to some function of x. All right, so it tells us to start with the momentum equation. So we go to the momentum integral equations from that section that I pointed out in the book, and then we have functional relationships for the constants C1 and C2. So using that same substitution, we can solve for C1 and C2, and we come up with a value of C1 of 2/15 and a value of C2 of 2. And I know I'm going through this rather quickly, but if you need to rewind it, you'll be able to. So that's kind of what I'm banking on. All right, so going back to the same equation and plugging in, we also know what REX looks like for this. So we can substitute that in, and we can find a boundary layer thickness, and del over x is going to equal the square root of 30 over the square root of REX. So based on those two ideas, the definition of REX and the momentum integral equation, then we are able to come up with an expression for the boundary layer thickness. All right, so problem 925 looks very similar. Still want to use the momentum integral. You want to use those equations for C1 and C2, and you want to use the U over U substitution and the Y bar, the Y triangle substitution. And then you can, to do for comparison to table 9.2, which is what they ask you for, here are the reparator functions that you will want to use. All right, so ladies and gentlemen, that is our vodcast for section 9.2. It's also our last vodcast for fluid dynamics. It's been a pleasure, and I hope that you've learned a lot, and I hope that you are ready to go on to the next class. I sincerely think you are if you've done the work, and I look forward to working with you in the future. Thanks.